All right, everybody. Let's talk a little bit about this Eduastic Leap 2025 Algebra 1 practice test. So, this is the same practice test that is on Louisiana Believes, and there's been some other videos about it. So, if you find one of the videos that has the same practice test, that's good information too. I feel like they go through the stuff a little bit fast and don't explain why. I'm going to try to explain why and give you strategies on how to find the answer quickly, and also probably go over the longer routes if you want to make sure the answer is completely confirmed. So this first one says determine all the zeros for the function that this f of x equals all that jazz. Drag and drop all zeros of the function into the box. Okay, so you're going to drag and drop those. I'm going to go ahead and just circle it because this is a PDF. So what we really need to do is we need to figure out zeros to this. So that's not, there are infinite solutions to an equation like this. So in this case, we're saying that our y is 0. Okay, so we're looking for the roots of it. So when you look at a graph of something like this, it might look like that, and then like that, or like that. It could look like a lot of things. It's likely going to look more like this, but even if it's like flipped over and all that kind of stuff. It's your typical cubic parabola. So to find these, we're going to have to figure out some method. And one method that we know is the exploiting the zero factor property. So we've got all this jazz, x squared plus 2x. So we've set it equal to 0 because that's how we can find our zeros. So we're trying to find our roots where it hits that x-axis, and then it hits that x-axis whenever y is equal to 0. That's why we turned f of x to 0, because y equals f of x. These are effectively the same thing. So in this case, we're going to kind of use our zero factor property. Now, I don't have a lot of real estate to write stuff over here, so I'm just going to kind of use this spot right here. So one way to do this is to make sure it's all factored out, because one property is the zero product property. So the zero product property. And that says if you have any number of factors, usually we just write it like this. If we have any number of factors and they're things that are multiplied together, there can be more. It could be A, B, C, but it doesn't really matter what it is. If it's usually written as A times B equals 0, then the only way this can be true is either A equals 0, B equals 0, C equals 0, or all three, or any combination of them. So it could be, and let's test this. So it could be if A is equal to 0 and B is equal to like 2, I'm just coming up with random stuff, and C is equal to 3, then that would be 0 times 2 times 3 equals 0 times anything is 0, so that does equal to 0, so that would be true. This is always true because if you are multiplying stuff and one factor is 0, then the final answer is always 0. There's no way to multiply by 0. It's the multiplicative annihilator, which is a fancy name. So we kind of already have one of them, but because these are going to act as their own little factors. It might be a group of stuff, but at the end of the day, when you have an x value in there, it's just going to be a number. The only thing that we have to really worry about is this part, because this is not easy to look at. It's not already factored. So if we want to factor this, we're basically saying each one of our factors has to be equal to 0. And my other factor right now is that. So we're sitting there with this has to be equal to 0 and this has to be equal to 0. But this right here needs to be factored to solve it. Now, we could use a lot of different things. We could use the quadratic formula, or we can factor it by grouping, or, whatever you want to call it for quadratics. But no matter what, we're really just looking at breaking this up into some x minus or plus something times x minus or plus something. So we need to figure out what that is. So one strategy that we have is we look at the coefficient of our first term, which is a 1 if it's not written. It's whatever number that is if it is written, but right now it's a 1. So we have 1x squared if there's no coefficient already written. And then we look at our final term, our constant term. So we're going to look at this and this. So we need something. We know from what happens when we distribute, kind of thinking in reverse. Remember, factoring is reverse distribution. So we need to think of it in reverse. So in this case, we need to figure out something that when you multiply them, you get what this is. So 1 times -8. So we need to have two numbers. Let's say it's an A times B is equal to -8. So we need two numbers that multiply together to get -8. And because of the way distribution works, add together to get this number, 2. So two numbers that multiply together to get -8 and add together to get 2. So if I list out my factors, my possible factors, it could be 1. So let's look at it. 1 and 8. It could be 2 and 4. 4 and 2, it's just reversed. So it looks like there's only those. So it could be 1 and 8, because those multiply together to get 8. And 2 and 4, those multiply together to get 8. Now our sign, our sign is negative right here. So one of these is going to have to be negative, but not both. So it could be like that. It's all kinds of possibilities. So it's going to be 1 and 8, 1 and -8, or -1 and 8, -2 and 4, or 2 and -4. One of those. So we look to this. They need to add together to be a positive number. So we know whatever we do, the bigger number is going to have to be positive, because that's the only way this can add together to get +2. So when I look at this, it's clearly this. It's clearly that. So 2 and -2 and 4. And again, I got -2 and 4 because, again, these two multiply together to get -8, and they add together to get +2. That's how you figure out what sign, which number has to be, which number has what sign. Now, again, if this was positive, if this had been a positive number, the only difference here would be that both of the numbers would have to have the same sign, either positives or negatives. But in this case, if they multiply together to get a -8, one of them has to be negative, not both. So we can rewrite this as x minus 2 and x plus 4. You're always able to break up your quadratics like that. So if this had been a different coefficient, we would have had to factor by grouping. We would have had to break up this term into those two things and go through all of that. But that's not what the problem is asking right now. So this whole thing right here, and just for funsies, I'm going to confirm whether or not this is true. Does this, when you distribute it out, does this give me the same thing right here? Does it give me the left side of this? Because that is our goal. We're thinking about it in reverse. Our goal was to get it to look like this, but before I start working with this, I should probably confirm that I did it right. So let's see. X times x is x squared. X times 4 is positive 4x. -2 times x is -2x. And -2 times 4 is -8. And then when I combine like terms, which is the same thing as this. So I must have done it right. What's nice about algebra is there are so many ways to confirm almost every step that you're doing. So this and this must be true at the same time. And again, just kind of getting rid of this a little bit. We're really just expanding this, factoring this. So really our original equation kind of looks like this now. That's this part. And then that x minus 6 has been there the whole time. So if you don't do it in the same order, if you don't start solving with that first, it's fine. You can sit there and just, you've basically written it in a form that is convenient for the zero product property. So we know that using the zero product property that x minus 2 is equal to 0, or x plus 4 equals 0, or x minus 6 equals 0. Or all three. It won't work that way normally, but because your x is only going to be one thing at a time. But let's look at this. Let's add 2 to both sides on this one, and we get x is equal to 2. So I've got my answer for that one. And then let's subtract 4 from both sides on this one, and I get x is equal to negative 4. Okay. And don't worry, we're going to confirm all of these in just a second, just to make sure. It's always good practice to confirm. And the more you that's the reason that we want practice a lot, is to get fast at this so that we don't take a lot of time. But either way. So this should be true. So let me go back to the original equation and confirm that I didn't goof something. Let's plug in 2 and make sure that our left and our right side of our equation are the same. So we get 2 squared plus 2 times 2. I'm just replacing x with what I'm alleging that it equals to, 2 minus 6. All right, so 2 squared right here is 4 plus 4, because that's 2 times 2, minus 8. And then this right here is negative 4. I'm just kind of simplifying as I go. 4 plus 4 is 8. Now, obviously, you don't need this many lines, but 8 minus 8 is 0, negative 4. 0 times negative 4 equals 0. So this one is true. So this one is true. Let's try plugging in negative 4. Confirming your solutions is usually a really good idea. But now I'm just going to replace my x with my new x to see if this is still equal to what I need it to be. And so I get negative 4 squared is positive 16. 2 times negative 4 is negative 8. And we still have this minus 8 over here. (16 minus 8 minus another 8 is indeed equal to 0. Negative 4 minus 6 is negative 10, so 0 times negative 10 is also 0. And then last but not least, we can plug in 6. But again, it doesn't. One thing that we can do to abbreviate this process, it doesn't matter what this factor is equal to. When I plug in 6 right here, I get 6 minus 6 is 0. So at the end of the day, regardless of what number this equals, just like the previous ones, you could have done it the fast way in the previous ones as well. Regardless, if I plug this in right here, I get 6 minus 6 is 0. And whatever this is, it's going to multiply times 0 and become 0. So all 3 of these have been confirmed. So my answers here that I will drag and drop are 2, negative 4, and 6. Now, if you want to know a fast way to do this, plug them in to the original. One fast way to do this on a test like this is, even if you don't do the zero product property, you can just plug in each one of these. So I could have gone to the original It takes a little bit of time, but I can kind of look at it and I can say, well, automatically I know 6 is going to be one of them. So I've got a third of my solutions. And so I can say, all right, well, let me try plugging in some stuff. I always like plugging in 0 first. So if I plug in 0, I get 0 plus 0 minus 8. So negative 8 times 0 minus 6. So negative 8 times negative 6 is positive 48. Well, it can't be that. So I can discount this one. And then I can try plugging in 4 and realize it won't work. Maybe I plug in 2. Start with low numbers. The low numbers are usually pretty easy. It's unlikely to be this because you're going to have to square it. But either way, who knows? Some equations could be. But again, I like trying to plug in some low numbers. If let's just say you get tested anxiety and you completely throw out your name and every single thing, like SpongeBob. We threw out the name! Sometimes just, defaulting to try plugging in stuff. If the left and the right side are equal, if it's 0 equals 0, then everything's good. And you can find solutions to these. All right, on number 2, which expression is equivalent to that jazz right there? Well, this one's actually a lot easier to the other one. We only have one correct answer here. So all I'm going to really do is I'm going to go ahead and just combine like terms. I'm going to distribute and combine like terms to see. I want to make sure I can simplify this. And so in this case, we need to get rid of those parentheses. So there's an invisible 1 out in front of this. And then if I distribute a 1, it doesn't do anything. So my parentheses go away on that first part without changing anything. But then I've got this little invisible negative 1 right here. That negative is still just saying that there's a minus 1 of this group over here. So when I distribute this onto both of those, I get a negative 7x squared. And then negative 1 times negative 6x cubed is positive 6x cubed. So I combine like terms. Remember when you combine like terms, you can only combine like terms and simplify that way by adding and subtracting if they have the same number and type of factors, okay? So this is an x to the 5th. I don't see any other x to the 5ths over here, so I can't combine it with anything. And already, without even doing anything else, that at 3x to the 5th can't combine with anything, so it can't disappear. So we can already discount this answer and this answer. So I've already kind of gotten rid of half of my half of the other things. So let's try combining these. So I notice that I do have another x cubed term, and I have 8x cubed plus 6x cubed is positive 14x cubed. So without even finishing it, I know it can't be this one. So I've already got my answer. But if we finish it, it's got to be like this because this is an x. An x. Oh, wait. Did I write my stuff wrong? No, I didn't. I've already combined this. My bad. So we've done this part, we've done those parts, and now I just bring this down because it also doesn't have anything else to combine with. So it must be this. Which graph best represents the solution to this system of inequalities? So there's a few ways to do this. We've got several different graphs. So you could just go ahead and on scratch paper try to graph them and see what they look like. That works. And if you wanted to graph these lines, you'd basically just find an easy way to do it for this in this form is to find your x and your y intercepts. So for this first one, x plus y is less than or equal to 6. If I want to find my x-intercept, where it hits my x-axis, so I don't know which graph it is, but if my x-axis intercept, my x-intercept is when it hits the x-axis, and that only ever happens when y is equal to 0. So for your x-intercept, y is equal to 0. Similarly, the same thing for your y-intercept, it has to hit the y-axis, which only ever happens when x is equal to 0. So if you want your y-intercept, set x equal to 0. If you want your x-intercept, set y equal to 0. They're just fancy words for saying this is where it hits that axis. And remember, your axis is the special line where the other variable is equal to 0. The y-axis is just the line x equals 0. Everywhere on that line, it's equal to 0. And same thing for your x-axis, your y is equal to 0. So I've belabored that because students have like this, they kind of get confused. They think magic's happening. That's the only thing special about those lines at all. And those aren't the only solutions to your equations. But when you have a system, it is a lot of times. In this case, we have a potential infinitely many solutions because these are inequalities and it's a system. But either way. Now, so when I look at this, for that first inequality, it seems like they hit each other at the same spot. So for that first inequality, when x equals 0, y has to be less than or equal, or y has to be, for just the intercept, it's only going to be 1 point where it hits that. So y is equal to 6, okay? So when I look at this, the point 0, 6 has to be somewhere on my graph. That can't be it. That can't be it. This and this are the only ones that it could be. So it couldn't be this one. That point is not even on that graph. That point is not even on that graph. So it can't be those. You can get rid of half of your solutions now. And if I also do that for my x-intercept, when I set y equal to 0, x has to be 6 to find my my y-intercept. So for my y-intercept, x equals 0, that's this part. And for my x-intercept, y equals 0. So if I set y equals 0, I can see where my x-intercept is. So let's see. This one does work because when I set y equal to 0, x has to be 6. So that's clearly on there, and that's clearly on that same line. So it seems like this is that first line. Now again, this will go faster when I'm not explaining the whole thing. When you're actually doing it, it's just like, okay, well, let's see. Let's just analyze the intercepts instead of graphing the entire thing. Now, graphing the entire thing, you would do your intercepts, and then you would connect the dots and make your line, and then you decide which way to shade. But in this case, when we're just trying to solve one of these things with multiple choice, a good strategy is to kind of throw out what it can't be first. So let's look at this. X plus 2y is less than or equal to 8. If I want to graph an inequality, I have to graph the line first. That's why I had that equal sign on the previous one. I have to graph the line first and then decide which way to shade. So again, for my x-intercept, y is equal to 0. So I have x plus 2 times 0 equals 8. So x equals 8. So I have the point when x is 8, y is 0. That is my x-intercept because I set y equal to 0. I could have discounted it with this as well. So it looks like that. But and that point has to exist. So I automatically know it can't be that one. It can't be that one. Okay? Because when I go to find my x-intercept, my bad. Y was 0, x right there. So that point must exist on there because these are inclusive. They can equal. So that point must exist. I have this equation. I have found the x-intercept. I have set y equal to 0, and I have found the x-intercept. So I have the point 0, x right there. So that point must exist on there because these are inclusive. They can equal. So that point must exist. I have this equation. I have found the x-intercept. I've set y equal to 0, and I have found the x-intercept. So I have found the x-intercept. I have found the x-intercept. So when y is 0, x is equal to 8. So I graph those 2 points. This point is on this, but this point doesn't even have a line going through it. So that's one way to get rid of the answers it couldn't be. So it can't be that one. So it must be D. It must be D. Now, honestly, I could, maybe all of them have the exact same thing. But another way to do this, to discount some of these things, that's a pretty fast way to do it. Sometimes you have all 4 of them having the exact same thing. You're just trying to identify the shading. But in this case, that's not what we have. But another way to have done this is I could have went to graph my line, and I could have put it into slope-intercept form. So if I'm graphing the line, I do that first before I decide which way to shade. Subtract x from both sides because I want it in slope-intercept form. And I get negative x plus 6 or 6 minus x. It doesn't matter how you write it. So notice that this has a negative slope. Negative slopes always look like something like that. It could look like that, or like that, or like that. But going from left to right, it goes down. These are the only 2 that do that. So you could just analyze the slope. I've got a -1 slope on one of my lines. This C does have a -1 slope on one of the lines. I go down 1 over 1. This one also does. So I don't know which line is which in this case. So both of those work, but this strategy is before you've done any of this. And we can discount this and this for that same reason, because both of those have positive slopes. So both of these could work. Maybe you highlight those in some way. Now let's analyze the slope of the other line before we've decided about shading. So if I look at this, x plus 2y is less than or equal to 8. Now again, I graphed the line before I decide which way to shade, so let's just graph the equal part of that. So I'm going to subtract x from both sides, and I'll get 2y equals 8 minus x, or negative x plus 8. They mean the same thing. Maybe you write it as -1x. It doesn't matter. Remember, negative x is the same thing as -1x. I like doing that because I can see what my slope is. So then let's divide every term by 2 to get rid of that. And I get y is equal to -1/2 x, or -1x over 2, whatever. The slope, different ways of writing it doesn't change anything. My slope is -1/2, so I go down 1 for every 2 I go to the right. So my other line goes down 1 for every 2 I go to the right. So that would be right there. So it can't be this one. So another way of discounting something. Don't pattern match and say, well, there's a 2 and there's a 1. So remember, it's your change in y, your rise, over your change in x for your slope. That's what slope means. So it's your change in y over your change in x. So that's your rise over your run. So my change in y was a -1 over my change in x, which is a run of 2. So it means I can either write -1 as -1 over +2 or 1 over -2. Those are both the same. So this one right here says go down. So from a point, go down 1 over 2. This one right here, from that same point, says go up 1, left 2. They mean the same thing. So no matter what, when you're actually graphing these things, let's just take this part right here. If you had a point on one of these things, like right here, okay, if you had a point on this, like right here, it would mean go down 1 over 2. See how that's on the line? or go up 1, left 2. See how that's on the line? But those are just several different strategies. Now, the shading isn't going to be super helpful on this one. That you could look at the shading and say, put them both into slope-intercept form and say, or realize your y is right here and positive. It's right here, so it's less than, so you'll have to shade downward on one of the lines. And then this one right here, your y is on the left side, and it's it's less than, so you also have to shade down. So this one right here is shading down below this one and up above this one and finding the overlap. So it can't be this one, which similarly might have something else, but that didn't really help us. It only got rid of one of our solutions. But you wouldn't have to do all of this, and you wouldn't have to explain it to somebody. This goes a lot faster when you do it. So some methods of trying to figure out the answer for this are analyze your intercepts of all of these graphs and see if they match up. Another method is to actually analyze the slope. A lot of different ways to do a problem like that. Was this 3? Oh, I did 1, 2, and 3. Let A represent a non-zero rational number and B represent a rational number. Which expression could represent a rational number? So let's see. So it's looking for which one could represent a rational number. So we're really looking at what operations between two numbers. So we have A is a rational number. A is rational, which means that it can be expressed as a ratio instead of the number itself. So you have some decimal form of something, or something like pi, for if it were irrational, and A is rational, so it's not like pi or e or anything like that. So in our case, we can express it as a ratio. We can do some sort of jazz if we need to write it as a fraction, or a repeating decimal. So in this case, B represents an irrational number. So B could be a lot of different things. It could be this. B could be this. B could be the square root of 2. It could be a lot of different numbers. We don't care about that, but the behavior of it means a rational number can be expressed as a ratio. Rational numbers as a decimal end up being something like 0.3 repeating. We can make an algebraic equation to change this into a fraction, which you find out once you do it is 1/3. But pi cannot, or square root of 2, these are non-repeating. They don't have a pattern after the decimal place. So like pi itself is 3.14159, and some other jazz, like 268, and it just keeps going. And I would never suggest anybody memorize any digits of pi. This will probably get you to the moon. I believe 10 digits at the most is what you need to get to the moon with enough accuracy. But so I wouldn't recommend anybody memorize these things. But in general, when you go through and you analyze forever and ever, you never find a pattern. You never find it repeating. It just can't. So, and then this would keep going on. So let's analyze some things. When I look at this, I think of it as imagine we are dealing with pi. 2 is a rational number. What? 1, 5, 9, 2, 6, 8, ... 2 plus that just makes this. Notice the decimal place was not even affected by adding a whole number. And what's funny about this is it just turns out that when you add a rational number to an irrational number, it doesn't suddenly become a rational number. It's always going to stay irrational because those decimal places at the end don't necessarily become rational. Like you're not going to make a pattern occur, or else we would just always do that. We would never have to write a rational number if we could just add another number to it and then take it away or something. So like we would never have to write it like that. So this right here would not work. And in that case, this right here would not work because like if we could just subtract the irrational number from 0 and make it rational, that would not that would be amazing, but it doesn't work. Now, A times B. What ends up happening here, and again, I'm just using whole numbers because it is a rational number. It's an example of a rational number. But no matter what you do, multiplying a rational number times an irrational number, so like that, 2 times pi does not make it rational. It's always going to stay rational. So a rational number times an irrational number is always an irrational number as well. So it can't be that one. Now it could be this. It isn't always this. Do you notice how it says could? That just means that there exists some irrational numbers that will be that. Pi squared is irrational. Pi squared is irrational. It doesn't become rational because we have squared it. But what is interesting is that there are some numbers, like square root of 2 is irrational, but there are some numbers that when you square them, you get a rational number. So this is the only thing that could represent a rational number. Because we don't know what A and B are, we want to open up the possibility that this could happen. It doesn't mean that it always happens. Like pi squared is irrational, but square root of 2 squared is rational. So the existence of one possibility means that this could happen. And the reason we have this is often for proofs, because if I can find a single example, I cannot use it for a proof of something that always works. Okay? I might end this video because I feel like I'm going on for a little bit long, so I might start doing part B for B in the next one. But let's just look at it to see if this can be answered really fast. Consider a quadratic equation with integer coefficients and 2 distinct zeros. If one zero is irrational, which statement is true about the other zero? The other zero must be rational. The other zero must be irrational. The other zero can be either rational or irrational. The other zero must be non-real. All right, we have a quadratic equation with integer coefficients. Okay, so it's like a x squared plus... This might take a little bit longer because I want to explain why. This one I want to make sure you understand why. So I'm going to put that into the next video.